Okay, here we're going to look at an example that appears in your lecture notes on page 14. What I've done is I've filled in a lot of the details of the analysis that are going to go into drawing the root locus for the system that is shown. So be sure to download that PDF file and print it out before you start going through this video solution. In this example, we have a feedback loop where we have an open loop transfer function, which is given by the product of these two here. And recall that the closed loop transfer function, GCL, is always written as the open loop divided by 1 plus GOL. So with GOL written here as K times a numerator n, which the numerator is just 1, and D is that fourth order polynomial here. And again, what we want to do is find out where the poles of the transfer function, how they move as we change the gain there of K. Okay. So the first thing we need to ask ourselves is how many branches do we expect? That is, how many roots of the characteristic equation do we have for a given value of K? Well, we look back and we see that if our transfer function here has a denominator given by this, if you multiply this out, you get D plus K in S is a 0. So the order of the polynomial here on the left-hand side is really dictated by the maximum order of either n or d. And since d is fourth order and n is just a constant, we're going to expect to get 4 branches of a root locus plot. Now, probably the most fundamental thing to remember when you start out with your root locus plots is where they start and where they end. And this is always the case. They start out at the poles. In this case, we have 4 poles of our open loop transfer function. I've done the math here in terms of solving the open loop characteristic equation, which is s to the fourth plus 8s cubed plus 36s squared plus 80s. I solved that. Well, that was relatively easy to solve, because if you look back at the factored form here, we can see, yes, there's one at the origin, there's a pole of -4, and then I solved the quadratic equation to find the roots of that. So that's where the 4 poles come from. So that's where they start. We also know that the root locus branches end at either open loop zeros, and whatever is left over, the rest of them end at infinity. Well, being we have no open loop zeros, then they all end at infinity. So that tells us in advance we're going to have to do some work here in finding some asymptotes. Rule number 4, you might recall, is a very useful one. It tells us where on the real axis that the root locus is going to be. In this case, what we do is we simply look at the real open loop poles, or zeros, but here we have none. So we just look at the real poles, and we have 2 of those. So if you imagine those poles on the complex plane on the real axis, what we see is it has to be to the left of an odd number. So it's going to be definitely to the left of P1 and to the right of P2, but it cannot be to the left of P2, because P2, that would make 2 an even number there to the right. So this is a key thing that we're going to use in order to construct our plots. As I mentioned before, since all the root locus branches end at infinity, we need to find out what those asymptotes are. So we use those equations from Rule 5. We find out one where what the intercept is for these asymptotes. It's a very straightforward equation to use. You sum up your poles, a 0, minus 4, and our two complex ones. We have no zeros. We divide by the number of poles minus the numbers of zeros of our open loop system, so that's 4. So in the end, we find that that intercept occurs on the real axis at minus 2. The angle at which these asymptotes come away are found from this equation. Again, NP is 4, NZ is 0. So when we put this in there, we get an equation that says that we have our angles defined by this equation. So you start putting in integer values of k. K equal to 1 gives you 45. K equal to 2 gives you 135. K equal to 3, 225. K equal to 4, 315. If you put in higher numbers for k, like 5, you'll find that that cycle begins to repeat. So we just simply have 4 angles. Another important point, which is governed here by Rule 6, are the points where the root locus breaks away. It either breaks away from the real axis, or it might break away somewhere off of the real axis. But the key thing for a breakaway re-entry point is it corresponds to roots which are non-distinct repeated roots. That's effectively what you get when you set ds of n over d equal to 0. Well, we have a denominator, and so when we do the differentiation of that, we recall the quotient rule for differentiation. Basically, in this case, it's the minus the derivative of the denominator here on top divided by the denominator squared. Well, since we're trying to find the values of s that make that a 0, we can forget about what the denominator is and just solve for this. Unfortunately, it's a cubic equation. So here we do have to diverge a bit from our goal here of constructing these plots without doing any numerical work. We do have to find these. So I used the MATLAB routine of roots, found the 3 values of s are minus 2, and then this complex conjugate pair minus 2 plus or minus 0.245j. Again, these represents points in a complex plane where we expect to have repeated roots. Those are the breakaway or re-entry points. Also, oftentimes when when we're looking at where the root locus starts, we know it starts at the open loop poles. If those poles are on the real axis, we know that the departure has to be along the real axis. The only way you can leave it is if it meets up with another pole and then has a repeated root. But oftentimes, and in this case, as we've seen, we have some poles off of the real axis. So we need to do a little bit of work here on finding out at what angles that these branches come away from these poles. The equation we use is given back there in rule number 7 of the notes. For this particular case, where we have no zeros, it reduces down to this equation here. So let's look first for the departure angle from that pole we called P1, which was the origin. Okay, to use this equation, as it says in the notes, what we do is we replace all values of s here by the pole we're interested in, that's P1, like this, and the one that involves P1 itself, this angle becomes the angle that we're trying to find, theta P1, the angle at which the root locus comes away from that open loop pole. Okay, so we do that, we substitute that into there, and we get this. So I put in P1 minus P2, that's a 4, P1 minus P3, that complex number, P1 minus P4 is that. So we need to find the angles. Here we might want to review what this actually means. When you're looking at a complex number in the complex plane, And let's focus in on this one, 2 minus 4j. So the real part is 2, the imaginary part is minus 4. We're looking for this angle here, measured from the positive real axis. So in this case, take note that this angle is in the fourth quadrant. Okay, so be careful. You've got to get that right in order to get the correct angle. So just be careful. Do this. If your calculator happens to be one where you have available this function of a tan 2, all the work is done for you. A tan 2 is a function that exists in MATLAB and Fortran and C, where you basically give as an argument to a tan 2 the numerator and the denominator. So here you would give it a minus 4 and a 2. Anyway, what this works out to be is a minus 63.44 degrees. Repeat the process here for the inverse tan of 4 over 2. That's the first quadrant angle, 63.44. We take this equation and solve for theta P1, and we find out something maybe we already knew, that it's going to be going out at minus 180. Something we already knew is that it starts on the real axis, and so it's got to go out on the real axis. Repeat the same process for P2. And those details are given there. Again, cannot overemphasize the importance of getting the right quadrant for your angles. So carefully look at the signs of these in getting that. We find out that for that pole of minus 4, it starts out, it departs at an angle of 0. Same thing for P3. We find that it starts out at minus 90 degrees. Pole P4 starts out at 90. Okay, now the question is, does it ever cross the imaginary axis? Well, that's important to us because we know that if the transfer function has a pole over in the right half plane, we have an unstable system. Okay, so how do you find that? Well, this is a very straightforward idea. If you have your closed loop denominator D, from which you get your poles, if it crosses the imaginary axis, that means S is equal to an imaginary a number. So we're trying to find where it crosses, and we're trying to find at what value of K that it does. So by substituting S equal to J omega and expanding your different powers of J, in this case we get a complex number. That complex number is a 0. It's the root of the characteristic equation. So the real part must be a 0. That's this equation here. The imaginary part must also be a 0, so that gives us this one. So if we look at the imaginary part first, we see there's two values of omega where it does cross, omega equal to a 0. That's actually where it starts out at pole P1. But there is another value of omega for which it does cross, and that's when omega is the square root of 10. So we put those two values back into omega for our second equation, which is the real part. So if I take this equation and I solve for K, substitute in these two values for omega, find out that again it starts out there, and the other one, which is really the important one, happens for a gain of 260. So we've gone through all the rules. Now let's put those rules to use. So let's go to the page there with our plots. And let's think about what important information that we have gained from our rules. Well, if you look back at rule number 4, the results from that, rule number 4 said that the root locus on the real axis can only be between the two open loop poles of P1 and P2. So we know that that's part of the root locus. What else that we learn are the departure angles. So if I look at the departure angle here for P1, this is pole open loop P1, we saw that that departs at 180 degrees, so that makes sense. P2 starts out with a departure angle of 0, so again that makes sense. It goes directly to the right. If we look at pole P3, we found that the departure angle there was a minus 90 degrees, so it's going to go out here. If we look at pole P4, our analysis showed that it goes out at a departure angle of positive 90 degrees. So that tells us where P3 and P4 originally move. Okay, now if we look back at Rule 6. Rule 6, we saw that there was a breakaway point which happened at a value there of 2.45. Let me just check my notes here and make sure I got the right numbers here. Yeah, it occurs when the root has an imaginary part of 2.45, a real part of minus 2. So I go up to minus 2, make a little blue dot here. That's going to be my breakaway point here. And there was also one down here on the bottom, 2.45. Okay. Our analysis shows that the asymptotes, which I've already drawn here as dashed lines, are basically at 45-degree angles. So those are the lines along which all four branches must end up. So we're really in a position now to fill in the blanks here. What we know is that P1, we said, starts out with a departure angle of 180 degrees. P2, departure angle is 0. They meet here in the middle. So they have a breakaway point here. We found that one. That was at minus 2. And so this one moves up to the breakaway point here. P3, we know it starts out at minus 90 degrees, so it moves along this line here. So that's what the breakaway point means. The two roots are the same. Well, the breakaway point here at the top, we have something starting out to the right, something to the left. What we know is that from our rule number 8, that it crosses the imaginary axis here at square root of 10. So it starts at the breakaway point along from the branch that is shown. It passes through square root of 10, and it ends up asymptotic to the dashed line. So I'm going to do my best here to draw a nice smooth curve here. Again, the key points are that it starts at the breakaway point, it passes through square root of 10, and it becomes asymptotic to this dashed line. So the curve here on the other side is going to be passing through square root of 10 here, and it's like this. Okay. Now rule 3 says that the bottom is symmetric with the top. So we don't have to really do any additional thinking. We just make it just a mirror image of what's there. So it's going to cross over right somewhere around here, asymptotic to that, and like that. So what this shows how the poles move as we change the gain. Again, they start out at our open loop poles of P1, P2, P3, and P4. P1 initially moves to the left, P2 to the right. They hit each other. There's a breakaway point. They split. One goes up and one goes down. P3 and P4 start out at our departure angles that we saw, 90 and minus 90 degrees. And they move that way until they hit the breakaway point here. They split. One moves to the right, crosses over into the unstable part of the plane, becomes asymptotic to our dash line. The other one moves to the left. What's happening with P4 and the rest is just a mirror image of what's shown above. So in summary, this example is one which demonstrates the methods of root locus plots. And it also says, an important result here from rule number 8, is that whenever the gain, K, is larger than 260, it's unstable. So all this information on the shape of the root locus and things like that, the instability, was understood just by following our rules. We did one bit of numerical calculation, and that was really back there on rule number 6. In order to find the breakaway points, we had to solve a cubic equation. But other than that, it's just a sketch which is based on those rules.